Okay, we're continuing on with Investigation 6A. This is Part 3. And we have just answered Question 6. And now we're going to start talking about this third situation. And I am on page 6A-4, where it says Figure 2C. Figure 2C presents a planet, think Earth, so it's going to be a planet similar to Earth with relatively fast rotation. And the hemisphere scale Hadley cells described in Figure 2B are no longer stable. And y'all don't need to really worry about what a Hadley cell is exactly. But what you want to see is that you have more circulation cells set up and they're smaller. Okay? And with the exception of air in motion at the equator, remember that air moving freely across the surface of a rotating planet will exhibit motion along the curved path. This change in direction is observed because the motion is being measured relative to a rotating frame of reference, meaning, remember that the planet is rotating. This departure from straight line motion is referred to as the Coriolis effect. Okay, so now I'm on number 7. Caused by planetary rotation, the Coriolis effect is absent at the equator but increases as latitude increases, reaching a maximum at the poles. Its direction of action, to the right or left, is determined by the sense of planetary rotation. In Figure 2C, imagine yourself in space looking down on the planet's north pole. The planet would be seen to be rotating counterclockwise, as shown by the curved black arrow. So it would be counterclockwise. I know that's kind of hard to see. Okay, so let me see if I can help you visualize what they're talking about. They said that if you were looking down on the planet's north pole, and so I drew a very simple planet, okay, it's going to look like it's rotating counterclockwise, okay? And if that is the way that it's moving, then if you look at it from the south pole, it looks like it's rotating clockwise, okay? So if it's turning on its axis from the north pole, it's going to look counterclockwise, and from the south pole, it's going to look clockwise, okay? So that's pretty rudimentary, but that sort of gives you a visual of what they're talking about. Okay. All right. So back to question 7. It says, in Figure 2C, imagine yourself in space looking down on the planet's north pole. The planet would be seen rotating counterclockwise, as shown on the figure by the curved black arrow. Now imagine yourself looking down on the planet's south pole. From above the south pole, the planet would be seen to be rotating. Okay, here's North Pole, counterclockwise. So if we continue spinning this, okay, then if we look at it from the South Pole is clockwise, okay? Looking at it, North Pole, counterclockwise. See if I can keep turning it. South Pole, clockwise. Alright, so you should select clockwise. Okay, and then it says, applied to Earth, these opposite senses of rotation cause air moving horizontally to turn towards the right in the northern hemisphere and turn towards the left in the southern hemisphere. Okay, and now we're on number 8. Okay. Figure 2C shows that the intense heating in the tropics initiates rising air currents, and at upper levels the air moves to higher latitudes while being deflected to the right in the northern hemisphere or to the left in the southern hemisphere. By about 30 degrees north or south, the upper level air would be flowing either east or west and essentially piling up because it's turning because of the Coriolis effect. So this added air raises surface air pressure at those latitudes, meaning latitudes about 30 degrees north and 30 degrees south, which pushes air near the surface towards both lower and higher latitudes. Okay. The flows towards the equator produce what's called the trade winds, and those towards the higher latitudes contribute to the prevailing westerlies. Okay, so let me zoom out just a second. So we're up here in number 8. I do want you to take the time to highlight so that you know what the trade winds are, what the prevailing westerlies are. Okay, in the northern hemisphere, the south-moving surface air is deflected to the right by the Earth's rotation. Wind direction is named according to the direction from which the wind is blowing. Okay, so let me get a map back out and we'll show you whether we should name those the northeast trades or the southeast trades. So hang on just a second. Alright, so we're going to look at this map. This is actually a map that we did a few days ago, trying to show ocean circulation, but it also shows the black arrows represents the surface winds. So we're talking about trade winds. Those are the winds that blow between 30 degrees and the equator. 30 degrees north in the equator or 30 degrees south in the equator. So you can ignore the other arrows. Just pay attention to the ones in black for right now, because that's what we're worried about. So the trade winds are the winds that blow from 30 degrees back to the equator. And if you're talking about the northern hemisphere, you notice we said a minute ago that everything seems to curve towards the right and move in a counterclockwise direction in the northern hemisphere. So it's going to curve to the right and it's going to move from northeast to southwest. Northeast to southwest. And because we name winds according to where they blow from, we're going to call these the northeast trade winds. So here's your number 8. Wind direction is named according to the direction from which the wind blows, so that these northern hemisphere flows are called the northeast trades, because in the northern hemisphere, again, the trade winds are starting in the northeast and blowing towards the southwest. In the southern hemisphere, they start in the southeast and blow towards the northwest. Okay? But number 8 asks you about the ones in the northern hemisphere. Okay? On the fast-rotating planet, again, think about Earth. Hadley cells are confined to the lower latitudes. They're bounded at about 30 degrees north and south. And we want to know, is that an area where we generally have cloudy skies or clear skies? Okay, so they're bounded at 30 degrees north and south by generally what? Semi-permanent high-pressure areas, characterized by large-scale sinking air. Okay, well, I need to pause and tell you that generally speaking, in the places that you have rising air, like here at the equator, rising air is going to promote cloud formation, okay, because you've got air and moisture coming up into the sky, and you're going to be able to form clouds. Where you have air sinking, that's going to discourage cloud formation. It's usually going to be clear when you have sinking air, and it's usually going to be cloudy where you have rising air. So with that information, you should be able to answer this. Because it says large-scale sinking air. So at 30 degrees north and south, generally we're going to have clear skies, okay, and semi-permanent high-pressure areas characterized by large-scale sinking air. Okay. Averaged over time, atmospheric circulation in the middle latitudes reveals little, if any, detectable Hadley cell structure. Okay, you don't really need to know about Hadley cell structure. Okay, middle latitudes include the region where, according to Figure 1, oh, that's right, we're skipping this one, sorry. Write a big O-M-I-T across that one. Sorry about that. Okay, and let's move on to 11. That makes number 10 pretty easy. Number 11. At the highest latitudes, a polar cell, approximately centered on the pole, is thermally maintained. Air masses migrating from lower latitudes are sufficiently warm and moist to undergo convection at about 60 degrees north and south. So you have another area of rising air at 60 degrees north and south, where rising air flows poleward, cools, and descends. This cold, dense air produces high surface air pressure. This air pushes towards the lower latitudes. In the Arctic, which is the northern hemisphere, the Coriolis effect deflects the southerly flow to the right. In the Antarctic, which is the southern hemisphere, the Coriolis effect deflects the northerly flow to the left. So, whether in the northern hemisphere or the southern hemisphere, the circulation of the polar cells becomes, and we need to figure out what that is. So we're going to go back to our map. Okay? Here is the polar regions, from 60 degrees north up to the North Pole, from 60 degrees south down to the South Pole. And you notice everything in the northern hemisphere curves to the right. And because those curve to the right, they seem to go generally from east to west. East to west, east to west. Down in the southern hemisphere, everything curves to the left. And that makes it also go from east to west, east to west. So, because we're naming winds based on where they blow from, those are going to be flowing from east to west, and so we're going to call them the polar easterlies. Okay, join me for part 4, where I'm actually going to talk you through the remainder of the questions as we look at a simulation.